Hello guys and welcome to this joint SoCS-CPAIOR invited talk titled Combinatorial Optimization for Multi-Agent Pathfinding by Peter Stuckey. And I want to stress and highlight that this is the joint invited talk and because we built the program together between SoCS and CPAIOR. Unfortunately, we can't be together in the same place and at the same time for some very obvious and well-known reason. But now let's focus a bit on Peter and let's try to understand why Peter is the perfect person for this joint talk between these two communities, which are not very dissimilar, but are still different. Let's start from the obvious and the most known facts. So Peter is a professor in the Faculty of Information Technology at the Monash University and he has been AAAI Fellow since 2019, since last year. But the most important facts of the work of Peter are summarized here. So first of all, Peter has been bridging the gap for a long time between different communities. So he has been active in the fields of constraint programming, logic programming, combinatorial search, etc., etc. Also, he has been a pioneer of constraint programming. So he has devised, designed, developed, and also deployed solvers, theoretical analysis, the first fundamental textbook in the area. Of course, he has driven the development of Minisync that everyone is aware of, and I hope you are aware of as well. And if you aren't, that's the right time for Googling it and find out what is it. And he also devised the lazy close generation, which is widely used in a wide range of solvers and techniques. And on top of that, or shall I say, in all his work, in all his project, he has been very problem-solving driven. So he has always tried to find out what are the problems in the real world, in the applications or in the fields, and then devised project activities and techniques for solving them. And he has done that for a wide range of applications areas. So we can mention timetabling, databases, or network security, or system security actually, to mention a few. So Peter is, let's say, a well-rounded researcher, which has been working in different research areas and in different applications areas. So he is the perfect person for bridging the gap and helping to merge these two communities of CPAIOR and SoCS. And so, ladies and gentlemen, I'm leaving the ground to Peter. Thank you very much.
All right, I'm Peter Stuckey. I'm going to talk about discrete optimization for multi-agent pathfinding. So the true people responsible for this hard work are Graham Gange for Lazy-CBS and Edward Lamb for BCP. But I'd be remiss if not mentioning Jo-Young Lee, who's the sort of chief proponent of the CBS, and all three of these approaches are sort of fighting to be the best at MAPF. All the others are other collaborators involved with this work. All right, here's an outline of the talk. We'll first talk about multi-agent pathfinding. What is the problem? Why should we be interested in it? And then I'll look at a constraint programming solution for tackling MAPF, which is called Lazy-CBS. And then a mixed integer programming approach to MAPF called branch and cut and price. And then we'll conclude. So what is multi-agent pathfinding? Well, we've got an unbounded amount of time available, and we've got a grid called the map, and we've got cells which are either free or obstacles in black, free in white. We've got a set of agents. They've each got a start location and a goal location, and they need to go from the start to the goal. In each time step, they can either move north, south, east, or west, so just orthogonal movements, or they can wait where they are. And so up till now, we're just talking about single agent pathfinding. Really becomes multi-agent pathfinding because we've got to be worried about collisions. So they can't both be in the same vertex at the same time. And they can't also sort of both use the same edge in opposite directions at the same time. Right, so here they would never be in the same vertex at the same time, but it's also impossible because they would cross the edge. And our aim is to minimize the sum of the individual costs, so the sum of the path lengths. An alternate objective you can have is makespan, where you're minimizing the maximum of the path lengths. That's an interesting problem, but much easier. We'll also have some assumptions. We've got a centralized solver. It's an offline task, so we're solving the entire thing by one solver, and we're interested in the optimal solution. So why should we be interested in MAPF? So here's an interesting little animation for Peter Stone's website about an uncontrolled sort of an automatic intersection where all of the cars just goes through, changing their speed slightly. Well, it's not exactly MAPF, but you can see that there's a MAPF style problem that hides in the middle of this example. If we have a look, if you think that is, you know, the future far away from what's actually going to happen, well, actually there's some footage from a real life intersection in Ethiopia. So MAPF is an exciting problem. But actually its more realistic motivation is this is a really critical problem that underlies lots of things in robotics. In video games, we have multiple units that have to move around. There are transport applications. Warehouse management is probably the big one. Product assembly also has this kind of problem. And even the 15 puzzle is actually an example of a multi-agent pathfinding problem. And the big one is really the warehouse management. So modern logistics sort of relies on this ability that we can store a lot of things in the shelves, and we can have them quickly packed into individual packages by having the robots move the shelves to where we are. So multi-agent pathfinding is the quintessential multi-agent movement coordination problem. And although real-world problems, like in the warehouse, for example, are actually harder because we have task assignment to the robots and things like this, they always have this underlying difficulty. It's an NP-hard problem, and you might ask, well, do we need optimality? Okay, in practice we don't, but if we look at the problems that arise for the optimal version, they also hit the bounded suboptimal case anyway. So we're going to need to understand the problems that by looking at the optimal problem, we see what's difficult about this problem, and we're going to need to be able to solve that even if we're going to use bounded suboptimality. And if we use bounded suboptimal solutions, unbounded suboptimal solutions, then it turns out they can be very, very bad. So we don't really want to do that. All right, so what MAPF solving methods are there? So there's sort of basically three groups we'll look at. Just A star, the basic A star, I'll show you that first, and then conflict-based search, which is really the current state of the art, ignoring this work that I'm talking about today. And then we've got all these encoding or reduction methods where we use an underlying discrete optimization technology like SAT or ASP or CP to solve it. There's a lot of suboptimal methods, which I won't talk about except briefly later on in experimental results. So where's the A star approach? So the problem with A star approach is we've got n agents that can each be in V locations. So we've just got V to the n as a state space just to describe the state of our system. And then again, for each agent, we have a different move. And so the number of operators is also exponential in the number of agents. So you can see even for this tiny example here of the mouse is moving, we have an m squared state space to define it. And you can see this little example is this bottleneck here. We've got lots of different ways that the individual mice could go, which will still result in the same bottleneck. So conflict-based search was basically developed to resolve this problem. And the idea here is we're only going to plan each agent individually. And so what do? We plan each agent individually, ignoring the other agents. Now, if there's no conflicts, then we're finished, and we've got the best possible solution, so that's perfect. So otherwise, there's a pair of agents A and B, which use the same resource, which could be a vertex or an edge, at the same time. And then we split the problem into two. In the left child, A cannot use resource X at time t. In the right child, B cannot use resource X at time t. So we've got twice our problems. And then we're going to end up with a pool of problems. We're going to pick which subproblem to work on next, usually the one which looks the most attractive, so it has the least lower bound on its solution cost. And we'll replan for the affected agent. So exactly one agent will have had a new constraint added. We'll replan for it, and we'll keep doing this until we find a solution with no conflicts. And that will be the best one because we keep picking the best possible starting point. So on our tiny little mouse example, each of them runs their individual path to begin with. So mouse 1 goes straight there, mouse 2 goes straight there, and we find a conflict at location C at time 2. So we're in the root node of our search tree here. We're going to split that into 2. So on the left branch, mouse 1 can't use location C at time 2. On the right branch, mouse 2 can't. And then if we examine subproblem 1, the left branch, we'll replan mouse 1. So here, mouse 1 will go here, take a wait, and then go here. And we've solved the entire problem. We've got a solution of cost 7 overall, and that's the optimal solution. So it's nice. CBS can solve these problems, at least small problems like that, very quickly. Let's look at encoding reductions, and here I've just sort of picked kind of representative of the latest version for each technology. For mixed integer programming, this is actually exactly a multi-commodity flow model, and so there's lots of work on that in mixed integer programming, and it can use makespan and sum of individual costs, but it's very bad on the sum of individual costs one, and it was able to solve very small graphs with small numbers of agents. A SAT solution was developed which was good on small maps that could eventually beat CBS. So one thing that's true about the conflict-based search approach CBS is it typically solves very quickly, or it can get stuck and never really solve. So it was interesting that for tight maps, tight problems, the SAT solution could do better if it was given a lot of time. CP solution, the best CP solution is more analogous to the BCP solution I'll talk about later, because the key thing was that you have variables which are picking a path for each agent. But the work there was restricted to makespan, and even then didn't work on very large examples. The SAT modular theory solution, well, this is a lazy construction of the SAT model. This is obviously better than the SAT model, and it could beat CBS on tight maps with a small number of agents. And there's a recent ASP solution. Again, sum of individual costs, an even tighter model using the fact that ASP has a nice sort of modeling interaction that it can use. And it uses unsatisfiable core-based optimization, which is exactly what we're going to use in Lazy-CBS. It's actually occurred after Lazy-CBS. And so that's nice to see that some of the ideas that are being successful in other places are used here. Okay, but the problem with all of the encodings reductions, at least the naive encodings, is this. We have to have this sort of decision variable is agent A at position P at time T, right? And it's essentially, there's just too many of these. Like N is the number of agents, V is the number of vertices, T is the time bound. There's way too many variables. For our trivial example, we're sort of looking at 16m plus 20 variables just to define that tiny, tiny little example that I'm showing you there. And it's worse because a tight T-bound can be very hard to determine. It's order V cubed for sum of the costs if we want an a priori bound on how much time it takes. All right, let's look at a constraint programming approach to solving the multi-agent pathfinding, which we call Lazy-CBS. So the good thing about constraint programming is it's a kind of integrative solving approach. So we can hide subproblems inside global constraints, and we're going to essentially use that trick to re-implement CBS inside a CBS solver. And then you're going, well, what is the advantage? Well, we can take advantage of features of modern CP solvers that allow us to avoid repeated work. So here's Lazy-CBS. So essentially we have this abstract CP model of what's going on. We have a set of agents and a set of locations and a set of times we're interested in. Each of the agents has a start location and an end location, and then the variables that we're actually going to concentrate on are these cost variables. So for each agent, what's the cost of its path? They're going to have some variables to coordinate the agents, and this is a permitted variable. So for each location for each time, we're going to say which agent is permitted to use that location at that time. We'd also have similar ones for edges, but we'll remove them for simplicity. And then the model is just saying, well, what's the cost of the path of this agent, right, that goes from start to end, which satisfies the permitted constraints. Let's update the cost. And then we're optimizing the sum of the costs, obviously. And really, we've put all of the hard work in this cost to path global constraint. So we can implement a specialized propagator to update path costs. So the role of this global constraint is just to update the lower bound on the cost C. So we can do that by computing a shortest path P from start of A to end of A that satisfies all the permitted constraints. So that means that if we look at every location that the path visits at time T, then agent A is permitted to visit that location at that time. And that will find us the shortest path, and then that's clearly a lower bound on the cost of this agent. It might be that we have to add more constraints later on, and it will just increase the path cost. We could also make this update the permitted constraints, so fix them to be equal to A if it was using it, but we're not going to do that. We're going to rely on doing that lazily later on. And essentially, this is exactly the same algorithm as the CBS individual agent pathfinder, right? Finding a path under some constraints, or finding the shortest path under some constraints. But hang on, you think, why aren't we cheating? The size of the model is still this order nVT, right? We've got for each location, for each time, we've got an agent which can take n different values, here this variable, so it's really the same size. The way we're going to get around that is we're going to just lazily create these permitted variables as required. So we don't need a permitted variable if there's no overuse of the resource at that location at that time. A bonus of this is that max time is no longer required, right? Because we're going to create permitted variables at times where agents intersect. So that essentially will only talk about the times that are interesting. Right, so at key we only need permitted variables if we've ever seen two agents use that same location at that same time. And essentially this is exactly the same as the CBS strategy for adding constraints. So what have we done? We've just re-inputted CBS. The key difference is the search is not the same. CBS has a best first search, which has some memory requirements. Lazy-CBS has depth first search, which is much more memory efficient, but more importantly, it allows us to no-good learning. And this is going to avoid repeated work. And this is because there's a weakness of CBS, right? So think about this small example. There are two independent conflicts here, purple and yellow and green and blue. If we try and solve this with CBS, what happens? Well, at the root node, we pay no extra cost, and essentially we've got a solution with 44, all the paths are length 11. So we pick it, we look at these paths, and we find some conflicts. So we're going to split on one of them. Let's say we split on the purple-yellow one first. So we say, okay, at this location, U here, either purple gets it or U gets it, and that's going to increase the cost by 1. And then we're going to pick one of these children, let's say the left one, we're going to expand that. We're going to say, oh, well, now we've got a conflict still between green and blue at this position, the V here, and we're going to split, and both of those children at least add one more to the cost. But the problem is this guy here, the right child, looks more promising, right? So this is only one more to the cost of the thing, but it's still got this whole green-blue problem in it. And so we're going to resolve the green-blue just to prove that there's no solution at size 1. So it may look fine for 2 sets of agents, but if we have 50 sets of agents, we're going to solve 2 to the 50 problems, which is essentially really just 50 problems that we're going to solve many, many times repeatedly just to get to a best solution. So this is a problem for CBS, repeated work. All right, but we're going to fix that with Lazy-CBS, but before we do that, we actually have to admit first thing that CP is actually really bad at these objectives, which are sum of costs, which is the kind of thing we're going to do. But luckily, there's recent approaches to tackling this, stolen from MAXAP, which is called call-guided optimization. And what you do in a call-guided optimization is you assume the best possible solution. So in our case, we assume that each agent takes its shortest path, ignoring all the other agents. We'll find a contradiction in that, that's a core. We'll rewrite the objective with this knowledge and then assume the best possible solution under this rewriting. And then we'll keep doing that, finding new contradictions and rewriting the objective until we find a solution. The first solution we find is the optimal, just like in CBS. But in order to do that, we need explanation of failure, because we're going to basically make assumptions which are too impossible to solve, and then we want to find out what we assumed which was wrong in order to update this objective, find these calls. So we're going to need to explain when a path is too long. So imagine for this agent, we've put this upper bound of 5 on its path, and we currently have these 4 blocked places. So we can't be here at 1, here at 2, and here at 3. How can we explain why the path from S1 to G1 is at least 5? So we could explain it by saying, well, we use these 4 blocked paths, but then it's unlikely to be reusable in some other path. We want to find a minimal explanation, which exactly explains a smallest reason why this is the case. So we can do this. We start from G1 at time 5 and search backwards, and when we hit a blocked resource, we mark it. So we're going to hit all of these resources. We're also going to head out here, but then the heuristic is going to say, well, we can't get back to S1 time. Okay, so we just mark these resources. We don't mark this one. Then we start from the start at time 0 and search forward. And we're going to hit these 2 marked resources. So we're going to treat this unmarked resource as if it's available. And then we stop. And actually all the marked resources that we collected are actually a minimal solution as to why the path length from S1 to G1 is greater than 5. You can see there's no path that I can get of length 5 which doesn't go through one of these 2 positions. So let's run Lazy-CBS in action. So the initial problem, of course, we give a upper bound on the path length of each agent to be their shortest path. So their path length is between 0 and 9. And then we run our path propagator on agent 1, and then it finds a lower bound on the path length, which is 9, unsurprisingly, because we used that to generate the upper bound. And we run the propagator for agent 2, and we also find a lower bound of 9. It also generates an example path. And we see that in their example paths, there's this conflict. They're both trying to use this resource at the same time. So we're going to introduce a permitted variable for this resource. We say location U at time 5 has to be given to one agent. Now we can branch on this variable. So we'll set it to 1, right, which will allow the first agent to just do exactly what it did before, but the second agent won't be able to go through here, so it'll have to take a weight somewhere. And that will give it a lower bound of 10. So our path will be too long. Now we can generate an explanation, as I showed you just a moment before, saying, well, because it's not permitted to be here, its path length has to be good at 10. All right, so that fails the left branch. We'll go to the right branch. So in the right branch, the permitted variable takes the value 2. Now agent 1 has to take a weight. Its lower bound will be increased, and we'll get an explanation why that lower bound increased. It was because it couldn't take this position U at time 5. And then we'll resolve those two together to find this general fact. One of the two agents has to take a path length of at least 10. Right? And this is independent of all the other agents in the problem. Of course, there's none in this tiny example, but you can imagine there's lots of other problems, even agents that cross. This reasoning doesn't depend on any of them. And this is a global no-good that we can use to reduce search for the rest of the time. So let's look at our example again. We start off with a lower bound of 44, which is all the shortest paths of length 11, and we make these assumptions that the longest path you're allowed is this 11, because that's the shortest current thing, so ideally that's the best. Now we'll solve that problem. We'll find this no good, analogous to what we just did, saying, let's say the purple and the yellow, one of them has to have a path length of at least 12, right? Because they have this shared resource here. Now, we're going to introduce a new variable which is going to count the number of the purple and the yellow which take a path length of at least 12, which is called Z1, but we're going to restrict it to only allow 1. So this is essentially going to say one of them can take 12, but the other one can't. And we're going to raise their upper bound to 12 for both of them. So even though we're allowing them both to take 12, this assumption here says only one of them can. All right, but that's enough to solve the purple-yellow problem. So when we run with this set of assumptions, we can't get a purple-yellow conflict. We will get a green-blue conflict still, right? We'll get the analogous one in green-blue. We'll add a Z variable for that. We'll relax the upper bounds on these two. We'll also have pushed the lower bound up by 1 each time, right? Because we know that at least one of them has to take a length 12 path. And then we'll run with these assumptions. So all the agents can take path length 12, but only one of them, of the pairs, can take one of 12. The other one has to still take 11. And now we'll find a solution. And in fact, we've proved that that's optimal. All right, so that's Lazy-CBS in action. But hang on, you might say, well, hang on, independence detection could have solved this problem, right? Independence detection we can do by looking at the problem to begin with, and if we see that those agents never interact, basically we could solve the two MAPF problems separately. So that can be a bit tricky in general, but the difficult part of it really is as the number of agents grow, none of these agents really looks up independent. Once we add this red agent going across from here to here, it interacts with yellow and purple here and blue and green here, and maybe that makes the whole, sort of makes it hard to see that they're independent. Whereas the kind of things that we did with the assumptions, that was always going to generate information which was independent. So in comparison to CBS, well, it's very similar to iterative deepening CBS, which you can look for in ISHCAI 2020, in the sense that each solve explores a whole CBS tree. So it certainly explores more high-level nodes than CBS. Right? So it looks through and it'll end up building a conflict saying, well, I can't do it because of this. We lazily introduce the permitted LT variables, and which is essentially analogous to what's happening in CBS. But what ends up happening in Lazy-CBS is we maybe get to a leaf node where all of those variables take a solution, all of the constraints are satisfied. We've got a new conflict that we haven't seen before, and we'll have to add a new variable, and then we'll branch on it and keep going. The path propagator is essentially exactly the low-level search in CBS, but the key thing is that no-goods that are generated are universal, and that prevents repeated work in two ways. It prevents repeated work across subtrees, where we learn about a conflict over here, and then we see the same conflict over here. We just have the no-good to solve the problem immediately for us. And it prevents work in resolve. So here, remember, we solve, we'll get a no-good, and then we'll solve again, and so we're going to end up solving the kind of problem many, many times, but all of the no-goods we learned in the first solve will help us in the later solves. All right, so let's look at some brief experiments. So these are just copied from the original paper. I'm not trying to answer what is the state of the art of all three methods at the moment. I don't think anyone knows those conditions, although I'll talk about what I believe that to be at the moment. So if we take the original version of CBS as defined, it's pretty weak. CBS with heuristics is much stronger. eCBS is a version of CBS where it's just bound to suboptimal, so here 1% of optimal, but on this map, this small map, which is a 20 by 20 map with 10% obstacles, that bound isn't enough to find solutions, so eCBS is actually weaker than CBSH. But Lazy-CBS is much, much better than all of them, right? Being able to solve many, many more problems and having this decay of success much, much better. If we look at a game map, well here, eCBS is solving a much easier problem because the paths are long, and so actually it can solve very, very well. And we see that CBS is bad, CBSH is much better, and Lazy-CBS again continues to be much stronger as the number of agents increase. Basically because we get more and more of this repeated behavior that happens as more and more agents interact. If we add rectangle breaking constraints to Lazy-CBS, so this is the purple line above, actually we can get even better than eCBS. And we'll talk a bit about rectangle symmetries later on. Let's look now at a mixed integer programming approach to solving the MAPF problem we call BCP. So it's BCP because it's branch and cut and price. What this is a very complicated way of solving a mixed integer program where we lazily construct the linear model during solver. Nice thing is it's guaranteed to find optimal solutions and it's going to allow us to avoid this problem of a too big encoding. So let's look at it roughly. I'm trying to give you some intuition. So methods for solving linear programs are, if we've got a set of linear constraints with a linear objective, then I can solve it by the simplex algorithm for our purposes. There are other algorithms as well. When we solve an integer program, where some variables can take have to take integer values, then we need to add some extra features to this. So we solve the relaxation, we ignore the integrality with the linear program, solve with the simplex, and then we're going to get some variables which are meant to be integer, which are taking non-integer variables, and we're going to branch. And we also keep track of the best solution we found so far, and sometimes we're going to get to a node and say, well, we could never get, even though we haven't got an integer solution, it could never be better than the solution we found already, so we don't need to look any further. That's branch and bound. So branch and cut and price is a generalization of branch and bound, except that we're going to start with a tiny matrix describing the problem, and we're going to add rows, which represent constraints to the problem, and we're going to add columns, which represent variables to the problem, lazily as we go along. So I want to try and illustrate that very simply on this tiny example of a linear polytope. So how does the simplex solve this problem? It's going to start off with all the variables at 0, let's say. It says, well, is there a direction where I could improve the objective? So imagine the objective is coming out of the screen towards us. It says, okay, here's a direction I can improve. I go as far as I can before I hit a constraint, and then I'll stop. And now I've got another vertex on this polytope, and I'll look for another improving direction. So I've got another improving direction. I'll go as far as I can, stop. Okay, now I've got another vertex. I'll look, is there another direction I can go? And here I find none of the directions will improve the solution, so I stop. So that's the LP solution. Let's do the same thing in branch, cut, and price. So here we'll say, oh, we'll start with no variables, right, and no constraints. So now I say, is there a variable that if I introduced could let me have a direction which would improve? Oh, there is. X2 is a variable that if I introduced it would allow me to improve my solution. And since I've got no constraints, I'm sort of going to make it really, really big. So then I'm going to say, oh, hang on, I have to add some constraints that I've ignored so far. There's this one here. So that's going to bring back my solution to x2. And now I go say, well, is there another variable which would give me a direction, if I added it in, which would allow me to improve the solution? So it turns out if I introduce the x1 variable, I got this new direction, which is x1 and x2 together, which would allow me to improve the solution. But again, I've ignored some constraints. I'll find some constraints. I'll bring them back. And then I'll say, well, is there any other variables that I could add which will allow me to improve the solution? Turns out there's none. And I satisfy all the constraints, so I'm done. So, in fact, I've finished the branch and cut and price, and I never introduced the direction x3, the variable x3. And I maybe never introduced many of the constraints of the problem because they never were violated by any of the points that I looked at. So that's the rough idea of branch and cut and price. So let's have a look at it for the MAPF problem. So it's made up of three parts. There's a master problem or restricted master problem whose role is to select good paths for each agent using the linear programming relaxation of the problem. There's a pricing problem which is trying to find new paths for each agent which could give me better solutions. And there's a separation problem which is checking that the paths we've selected satisfy the constraints, and if they don't, adding in new constraints where they've been violated. So our problem graph, we have vertexes, which is a location time pair, and then an edge is a pair of these, which are one time step apart. So basically always go one step up in time. We could move one location, or we could stay where we are in the same location. And then a path is just a sequence of those vertices, right? And the paths we're interested in start at the start vertex and end at the end vertex. So the master problem is essentially going to be this way, at least theoretically. We're going to write down all the paths for the agent, which started at start location and ended at its end location. And we're going to introduce variables to represent the proportion of that path that we select, m to p. Of course, we only want to select one, so we really want them to take values between 0 and 1. But they're going to be relaxed in many times during the search, and so we're going to get fractional values out of these lambda values. Then we're going to have a constraint to say, well, for each agent, you select one path. And we're going to have vertex collision constraints so that each vertex is used by at most one agent, and edge collision constraints, so each edge and its reverse is used by at most one agent. So this is what the master problem looks like. So basically we're minimizing the sum of costs, right? So here's the path we selected for each agent, and we look at its cost and we sum those up. That's straightforward. Every agent must use at least one path. So we could say equal, so every agent uses exactly equal one path, but the minimization will make it equality anyway. There's no point in using more paths than one if you don't need to. And for each vertex we have, so this xpv is a constant, so if we look at this path, if it uses the vertex v, that is location time pair v, then this will be set to 1, otherwise it will be set to 0. And so this just adds up that all the paths we select don't use that vertex more than once. And similarly, we've got these edge variables. So for each edge, if it's used, this y1p, this yep is 1. And this is the reverse edge in the reverse direction. We sum this up for all the paths we select, and that has to be less than or equal to 1. So we don't use an edge and its reverse more than once. All right, so that is the master problem we want to solve. The problem with this problem, of course, is, okay, these sets PA are large, if not infinite, and this is the number of location time pairs, this is the number of edge time pairs, so this is a huge model, much too big to solve in practice. And the key recognition is we only have to work with a finite subset of these paths, right? There's no reason to think about using this red path here if the green path is okay, because the red path is just a slower way of doing the same thing. So there's no reason to think about most of the paths. So we're going to only keep a very restricted set of paths that we're going to consider. And we're only going to add constraints when they're violated, just like we only added permitted variables in the Lazy-CBS approach. So we end up with this restricted master problem where, notice, we're only looking at the current set of paths we've seen, right? And we start off with actually no constraints on resources and just say, well, every agent must use at least one path of the small set we start off with, which might just be a shortest path. That'll give us a solution, but then it'll have problems. So that solution might right? We pick two paths and he might overflow in a vertex. So we can look at each vertex, we look at a solution, we count how many times we use that vertex in the solution that we've built. So this is using the answer to the lambda p's. If it's greater than 1, then we're using it too much, and we have to add the vertex constraint in that was missing. Similarly, we can calculate for each edge how many times it's used in the current solution, and if an edge and its reverse are used more than one time, we have to add in that constraint for the edge and its reverse. So we add in constraints only when they're violated. And the most important part is the pricing problem. So we're going to use our existing A* code to find shortest paths, right? But not shortest paths with the path length of 1 step per step. We're going to use a modified cost of the path, which is the reduced cost, right? So we're interested in finding the shortest path with respect to this reduced cost, CPAIOR. And so this reduced cost uses essentially prices which are from the current solution in the restricted master problem, which tell it, well, it might be worth, right, it could be expensive to use this vertex because other people want to use it. So it ends up being more expensive to use this vertex than it was. It could be expensive to use this edge because currently other people want to use it. And so this is the problem. So basically we change the cost of edges and vertexes using these dual values, which are from the solution, the optimal solution to the restricted master problem. And we have to look for a solution. We look for any path which would give us a negative reduced cost, because that is a path which, if we introduce that variable, might be able to reduce the total objective function value in the current master. And for those of you who know the simplex, what it is it's like we're treating all of these paths as being variables, but they're all set to 0. They're all non-parametric. Also, they're all parametric variables at the moment. And this check, finding this reduced cost path, is saying, okay, if I introduce this path, then this variable could be an entry variable. It could enter in the basis, and so it could give me a reduced objective value. Now, the most important thing about this is if we can find no paths which have a reduced cost less than 0, we can actually prove that even all the paths that we haven't considered, none of them could improve the current solution. And so we found the optimal. And that's the really important part of this pricing problem. So that doesn't solve the entire problem because, as I said, we're only solving a linear relaxation of the problem at each node, so we can get fractional values for these lambdas. So we can take half of one path and half of another for one agent. So we need to eventually make sure that they're all 0 and 1, and the way we do this is we select a vertex that is fractionally used by an agent. So let's say it picks two paths, each at a half, and one uses this vertex and one doesn't. And then we say, okay, either the vertex has to be used or it's not used. So that splits the things into two. We can do that by setting lambda p to 0 for paths where it doesn't use the vertex, which we're enforcing, or here we set lambda p equal to 0 for the paths where it does use the vertex that we're not allowing it to use. And that'll eventually force all the lambda p's to get a 0 or a 1 value. So it's this three-part problem. We have the restricted master problem, which has a current set of paths, and it picks the best set of those using the LP relaxation. Right? Remember, every variable here, these lambda p's, represents what the proportion of that path which is selected in the solution. And it doesn't have to be 0 or 1, it could be in between. And the row constraints represent conflicts we've already seen, so we've added in a constraint to stop them. Now, the pricing problem allows us to find better paths, so paths that could improve this LP relaxation. And that allows us to add new paths in for each agent, or it may find there's no better path for an agent. And then the separation problem checks that with the new solution we've got, are we overusing some resource too much? And then if that's the case, we have to do some branching to get a 0-1 answer. So as described, that's our basic algorithm. In order to make it competitive, we actually have to add some improvements. We're going to add 2 classes of redundant constraint and hierarchical branching rule. So the first one is rectangle symmetries. So rectangle symmetries are really important in MAPF problems on grids, because if we think of this problem here with agent A1 has to go here and agent A2 has to go here, then there's lots and lots of paths for agent A1 and A2 to do it. But if they take any of their shortest paths, they'll always have a conflict somewhere in this matrix, this little rectangle. Right, so if they both go down, then they'll immediately conflict. If they go the opposite direction, then A1 and A2 might eventually hit here. They can do some other thing, they'll eventually hit here. Anyway, there's lots of ways they'll always conflict. So we're going to add a cut to remove all those possible paths. And the sneaky way we do it is this. We sort of say, okay, let's count. How many times does A1 go through this barrier, right, at the right time, through these edges, and through this barrier at the right time? So if it goes through both of these barriers at the right time, then it's taking some shortest path through this rectangle. Right, and we count how many times A2 goes through these barriers at this time. Notice it can only go through it really once and here once, right? And what we're saying is the total number of times it goes through is less than or equal to 3, which means that we can't, if both of them go through the barrier at the optimal time, then they're inevitably conflicting, so this is not a solution. And the nice thing about this constraint, it also handles cases where, say, we say half of A1 goes this way, and half of it goes this way, and half of A2 goes this way, and half of it goes this way. It'll still add up to too much. And so it will get rid of those constraints, those kind of solutions as well. Even though we didn't select a single path, we still get rid of it. So that's very, very powerful. Fractional corridor conflicts are even more interesting case. So we've got two agents A1 and A2, and they need to cross through this corridor. What will the BCP algorithm try to do? It'll say, okay, we'll move them together, and then at this stage, A1 will send half of itself across this edge, A2 will send half of itself across the edge, and the other half will stay behind, stay where it is. Now, if you look, in total, only one unit went across the edge, so that's not violated. In total here, we have half of A1 and half of A2, so that's not violated. Half of A1 and half of A2, that's not violated. So this gives you a very nice solution where we sort of cross each other magically by splitting into half and then going across each half at a time. And so the BCP will look for these solutions because they appear to satisfy all the constraints. So we need to add a cut to prevent that from happening. Essentially what we do is we count how many times A1, or how much, what proportion of A1 crosses this thing at time t, and how much crosses at time t plus 1, how much of A2 crosses at time t, and how much crosses at time t plus 1. And we know that there has to be less than or equal to 1 in general, because we can't go back and forth in just one time step. And that's going to prevent this thing where we sort of split into half and sneak ourselves across. Okay, the final thing is branching on path length. So this turns out to be a much better branching rule, and so all the branching at the top of the tree is branching on path length. We don't branch on anything else on vertexes until all the agents' path lengths are fixed. And this is because we typically have these kind of solutions where there's one path for agent 1 which goes straight to the target, and there's another one where it waited for half a step, and then went all the rest of the way, and it picks with half proportion each. And somehow this allows us to avoid hitting some resource overlap in some locations, or edge locations like we've seen before. So we end up with this very good cost of just half more than the optimal cost. So it looks very, very attractive, but we want to avoid this artificial kind of solution which we can never get. So we can branch and say, well, if agent's path length is less than or equal to 5, it's going to get rid of this delay one, and it's going to force us to take this one at full proportion. So we're going to set a lambda p variable to 1, so we're going to be closer to a solution. And the other half, we can say that the agent path length is greater than or equal to 6, and that'll analogously remove the first solution. We'll pick the second solution of proportion 1. So this much more quickly drives us towards integer solutions. So BCP has two versions. The basic one, which is just the branch, cut, and price, the vertex and edge separation constraints. We talked about the pricing problem solved by A star, which is still probably the most complicated part, and we're branching using vertexes. BCP adds rectangle and conflict cuts and corridor conflict cuts, and then we first branch on path lengths. So let's look at some experimental results. So we've got lots of different benchmarks on these 4 maps, standard maps, and we compare against CBSH, which is the CBSH that we talked about last time, with CBS with heuristics, and with the rectangle handling as well. And so you can see the first thing to notice is the basic version is actually terrible. It's worse than CBSH, right? So, which is, all this huge hard work to get to a very complicated algorithm which doesn't perform as well as the current state of the art is pretty terrible. But once we add our specialized cuts for rectangles and corridors and a better branching, then BCP is in fact very good. So you can see the success rate on these benchmarks is very, very high, close to 100% all the time. And another thing that we find is that many of these problems we actually solve at the root node. So we don't need any search apart from the search for the individual paths, but we add a number of paths, add a number of conflict cuts, and then we say, oh, we've found an optimal solution without any branching. So this is able to solve many, many problems very, very fast. Just to look in a little bit more detail, you can also see the behavior. So this is the graph showing how the lower bound increases as the search improves, and here's the upper bound. So one good thing about BCP, which is different from CBS or Lazy-CBS, is it can find solutions before it finds the optimal solution. So we actually have something we can use here until we prove optimality at this point here. We'll find the best solution here. And also we see this behavior. So here we start with an initial lower bound, which is just the sum of the individual shortest paths, but we very, very quickly push that lower bound up, right? And then it takes a while to do the last bits. Obviously, it's always the last parts which are the hardest in an optimization problem. But you can see that we have this behavior that we get some early solutions and we get very quick pushing of the lower bound. So if we compare to CBS, well, we have these advantages that we're reasoning at all conflicts and agents simultaneously because we've got a linear program which does that. We can immediately recall paths generated anywhere in the high-level search tree. So if we generate a path in this part of the search tree, it's available over there, which might help us solve the same problem over here. So it's a bit like the no-good learning. We can add other types of conflicts because we've basically got a constraint-based view of the world. And anytime we improve our MIP solver, we could improve. So maybe we can find a better primal heuristic for this. Different from all the other CBS problems we've looked at, it's any time. It gives you solutions before the best one. And it can have a tight lower bound even if it's found no feasible solution. That's the pros. The cons are, well, it's difficult to understand. I hope I've made it as easy as possible to understand, although I've elided many of the details. More importantly, it's really difficult to implement. So there are very few people in the world who do branch and cut and price implementations. Eddie is one of them. And it's because they're very hard to build and very hard to debug. So like 2,000 lines of code for the A* code, because it's non-standard A* because the costs change every time. 12,000 lines of code for the separators and the glue to the A*, and that's not counting however many thousands or millions of lines of code which sit inside the MIP solver and the LP solver. So these are non-trivial software things. All right, to conclude. So straight CP doesn't scale, so we can do a lazy CBS solution because we use logic-based Bender's decomposition, which is relaxing on the permitted variables, and lazy variable addition, which is not a standard feature of CP solvers, but we can build, and core-guided search, which is a newish approach to optimization using CP solvers. The straight MIP solution to MAPF doesn't scale, but we can solve it by using dancing wool decomposition. That's the column generation that we did. And using this specialized column generator based on low-level pathfinding and specialized cuts for the problem. So sort of trying to lift away from the MAPF problem, if you have a problem which is NP hard in your combinatorial search problem, then you should consider doing discrete optimization techniques. So you first try them straight out of the box because many times they'll work straight away without any problem, but there are lots of decomposition approaches from discrete optimization you might use, which might be able to solve a problem even if a straight out of the box solution doesn't work. And there's this kind of arms race in MAPF between this CP approach, Lazy-CBS, the branch and cut and price approach, and the CBS approach. So all of them have improved very rapidly over the last 2 years. And part of this is because ideas from one help the other. And so we discover something in one thing and then we push it to the other side, and that also helps. So rectangle symmetries were originally done for path planning from CBS, but now they're used in discrete optimization methods as well. The low-level search improvements and path planning are all usable in discrete optimization approaches. And other way around, corridor symmetries were originally seen in the BCP solutions where they were half corridor symmetries, but they're very important in general for MAPF, and they're used in path planning approaches like CBS too. Disjoint splitting, which is natural in discrete optimization approaches, also improves CBS. And depth first search, the stuff you can see in IshGuide 2020 actually improves the best first search of CBS as well. So I would love to say which is the best. I suspect at the moment BCP is probably the best of the solutions, but each of the approaches is so rapidly moving that it's often hard, to see which one's the best at any moment in time. I suspect it's BCP at the moment because Eddie has considerably improved it from the version I'm talking about here. And the last message is, okay, this core guided search that we used in Lazy-CBS is maybe a plug-in replacement of A*. So if you're using A* for some kind of combinatorial search where there's a combinatorial search space, there's poor heuristics and repeated subproblems, then maybe you should consider looking at a kind of Lazy-CBS, what we do in Lazy-CBS. Because basically all the ideas there are just essentially replacing A* by this core guided search with no good learning. And that can help us by exponentially reducing the amount of work we have to do. So that brings us to the end. I'll meet you online for questions.